Welcome to Chem 1A at Shasta College. This is a Chapter 3 screencast that is an introduction to molarity. When chemists use solutions, we typically don't weigh them out. We don't measure their masses, but instead we measure the volume of solution we use, and this means that we also need to know what the concentration of the solution is. Now, there are lots of concentration units that one can use, but for chemists, probably the most common solution unit is something called molarity. And molarity is defined as moles of solute, so this is going to be the substance that we dissolve into the solution, divided by liters of solution, which is going to be our volume of total solution plus solute plus solvent to make the solution. We often abbreviate this by capital M for molarity. N represents moles of solute, and we're going to have to remember that this is moles of solute. And then V represents volume of solution, and we're going to have to remember that that's going to be in liters. So let's look at an example. A solution contains 58.87 grams of potassium bromide. It's dissolved in 750 milliliters of solution. What's the molarity of this solution? Well, we have to remember the definition of molarity, moles of solute divided by liters of solution. And we know the milliliters of solution, so that's easy to convert to liters. And then we know the grams of the solute potassium bromide, but we're going to have to convert that to moles. So we take our grams of potassium bromide, use the periodic table, find that 1 mole of potassium bromide has a mass of 119.0 grams. That's the conversion factor that allows us to convert from grams of solute to moles of solute. And that gives us 0.4947 moles of KBr. Now, to get the molarity, we're going to have to take the moles of the solute KBr and divide by the liters of solution. So this is going to be 0.4947 moles KBr divided by 0.7500 liters. Remember, we have to convert from milliliters to liters. And then we divide and get our answer of 0.6596 moles of KBr per liter of solution. And it's very common to, instead of moles per liter, to simply use the symbol capital M. So we would report this as 0.6596 molar KBr solution, and the capital M represents the moles per liter or molarity. Now here's how we actually do this. Potassium bromide is not orange, but here it's shown, the substance shown in the image is orange just so you can see it better. But what you would do is you would determine the amount of solute you need. You'd add it to typically a volumetric flask, because we're going to need to measure the volume of solution pretty accurately. It's pretty common to have some of typically our solvent's going to be water, so have some water in here before we add the solute, or in this case we can just add the solute to an empty flask. Then we're going to add our solvent, and again typically it's going to be water. And we don't measure out the amount of solvent we add. We simply add enough to get the desired solution volume. And typically in a volumetric flask, there will be a line that represents your total volume that you want to get, and you will mix up your solution and achieve that desired total solution volume. Okay, now some things you're going to need to be able to do with regard to molarity is not only calculate molarity just straightforward from its definition like the previous example, but also use known concentration solutions of a known molarity, to determine the volume of that solution that you will need to get some number of moles, and vice versa, different permutations of this type of calculation. So here we have a question: what volume of a 0.6596 molar potassium bromide solution, the one that we just figured out how to make, how much of this do we need to provide 0.1500 moles of potassium bromide? Maybe we need this for a reaction. And we note what our definition of molarity means, moles of solute per liter of solution, and specifically we're going to apply it to the known concentration of solution we have, which is 0.6596 moles of potassium bromide per 1 liter of solution. And here I'm writing it explicitly as a ratio, which can be used as a conversion factor. So we want 0.1500 moles of KBr, so that's the first thing we'll write down. And then our conversion factor allows us to convert from moles of KBr into liters of KBr solution. And notice we're going to be writing the molarity ratio sort of quote-unquote upside down because we want to cancel moles of KBr and we want to get a volume. So there's our setup. We're going to take 0.1500, multiply by 1, and divide by 0.6596. That will give us our answer, in this case 0.2274, and it's in liters of the potassium bromide solution, and specifically it's of the 0.6596 molar potassium bromide solution. And of course we could do a similar calculation, but turned around a little bit, if we were trying to find out the number of moles in a particular volume of solution, for example. Now what often happens is we have an existing solution of a particular substance, but we need a different concentration of that solution. And if what we need is a solution that's more dilute than our existing solution, then there's a fairly straightforward way to figure out how to make the more dilute solution, starting with the existing more concentrated solution. And here's an example. We have 0.6596 molar KBr, and we'd like to make 500 milliliters of 0.2500 molar KBr. Now, we want 0.500 liters or 500 milliliters of this KBr solution, this new KBr solution we want to make, and it needs to be a concentration of 0.2500 moles of KBr per liter of solution. And that conversion factor and those two bits of data allow us to determine that what we need is 0.1250 moles of KBr in the 500 milliliters of 0.25 molar KBr solution we're going to make. Now, where are we going to get that 0.1250 moles of KBr? Well, we'll get it, of course, from the more concentrated solution. And so what we do is we say, well, we need 0.125 moles of KBr. The more concentrated solution has 0.6596 moles of KBr per 1 liter of solution. So we can use the molarity value as a conversion factor. It's kind of upside down in a sense because we want to cancel out moles and we want to get liters. And when we do this calculation, we find that we need 0.1895 liters of this more concentrated 0.6596 molar KBr solution. And if we use that, add water to it, and dilute it appropriately, then we will make the amount we want of the more dilute 0.2500 molar KBr solution. So the actual how we make it description is we would combine 0.1895 liters of the more concentrated 0.6596 molar KBr with as much distilled water as is needed, so enough distilled water to get a total solution volume of 0.5000 liters. Again, take a look with a not exact representation. Here we have a solid when in fact we're using a liquid, but just for visual purposes, what you'd be doing here is taking a known quantity, calculated quantity of our concentrated solution, put it in a flask of the right size, add enough distilled water until we make the total solution volume that we want. Now, this is a very common thing for chemists to do, to take a more concentrated solution and to add water to it to make a more dilute solution. And the calculation involved in this type of dilution is going to pretty much always be the same type of thing as we just did in the previous example. And for this reason, we often use a sort of shortcut calculation This is fairly easy to show that's true in general, but for dilution, if we have a more concentrated solution and a less concentrated solution we like to make, then the molarity times the volume of the more concentrated solution is equal to the molarity times the volume of the less concentrated solution. And this M1V1 equals M2V2 equation, it's true for dilution in general. It's not true for everything in the world, so be careful about that. And if you remember this, you can always do kind of a plug and chug type of dilution calculation. So let's go back to the problem we just looked at, and let's do it that way. So our equation is M1 times V1 equals M2 times V2. And we could do it either way, but we're going to pick, for this case, we're going to pick that solution 2 is our more dilute solution. So it has a volume of 500 milliliters that we want and a concentration of 0.2500 molar. And then the more concentrated solution we're going to call solution 1, and we know its molarity, 0.6596 molar, but we don't know its volume. So what that means, of course, is we need to solve for the volume of solution 1, which of course is molarity times volume of solution 2 over molarity of solution 1. Molarity of solution 2 is 0.2500 molar, and volume of solution 2 is 500 milliliters, so we're going to make that liters, 0.500 liters. And then molarity of solution 1 is 0.6596 molar. And notice molarities cancel, leaving us with liters. And when we do our calculation, what we get is 0.1895 liters, and then we have to remember that this is 0.1895 liters of the 0.6596 molar KBr solution. And so how we would make this solution is, as before, combine the 0.1895 liters of the 0.6596 molar KBr solution with enough distilled water, so DI, deionized water, to make a total of 500 milliliters or 0.500 liters of total solution. So that is our final answer for the description of how to do this, and of course it agrees with what we did previously. And that's it for Screencast on Introduction to Molarity.